Okay, it thinks it's recording. Let's see how this goes, shall we? All right, so let's throw some light on the situation. Sorry, Mark, you can't see the screen. That's okay. It won't be too necessary at this moment. Drive and ambition. And courses. And what class is this? Starting to 311. And 2016 spring. And share it with students.
That's
and
us.
yes. And ISM star formation.
Yay.
Yes. And slideshow evolutionary tracks.
And
Well, here we go. For those following at home, this is slide number 39. There it is in all its glorious glory. Yes, I'm making a video, I think, with my iPad, which I've never tried before since I haven't borrowed anything since. Mark isn't here. Hi, Mark. Everyone say hi, Mark.
Hi, Mark.
Hi, Mark.
Also, during the video that you recorded for me, I did laugh when you all were trying to find that shot.
Oh, good. Did you know where? Excellent. All right, nice.
Why did he put it down, it's rolling, how can you not see that?
Yeah, well, yeah. Turns out that's easy to see when you're watching the video after the fact. Yes, well, what can we say? All righty then. So, protostellar evolutionary tracks of various masses. Notice that the ones high up there for high mass stars, they're pretty much horizontal. For low mass stars, the 0.5 solar mass star is nearly vertical. And for the solar mass star, it's vertical for a while, and then it does the dipsy doodle. It kind of goes woo, and so we're going to talk about why it goes woo. Yes, and then notice that the 15 solar mass star forms in about 60,000 years. The 9 solar mass star about 150,000 years. The 3 solar mass star about 3 million years. The solar mass star about 30 million years. The half solar mass star about 150 million years. Anybody seeing a trend here?
Nope.
Nope. Okay. Well, then let me point it out to you. Higher mass stars form faster, stronger gravity and all that. So higher mass stars do everything faster. They collapse to from protostar to full-fledged star faster. Then they live their lives faster. So it's all about, you know, they're flashes in the pan. Live fast, die young, burn brightly, all that kind of good stuff. So let's talk about some details in all of this here. So, racy. Three main sequence evolution. So first thing, once the protostar becomes optically thick, the rise in temperature produces a rise in pressure, and the collapse achieves a quasi-equilibrium configuration. We talked about that once it's no longer transparent, it's no longer free-falling, it's no longer doing the homologous collapse thing. So it never actually does make it down to a point all at the same time. Protostars do not collapse directly into black holes, in other words. Instead, they slow down when they become optically thick, and then the collapse starts proceeding on the Kelvin-Helmholtz timescale. And I'm trying to remember, did I ever have you guys do the problem where you estimate, like, how long would the sun last if it were shining only via gravitational radiation, right? And we found out, was that?
That sounds familiar.
Yeah, and we found, so basically you say, remember you say assume that the sun started out at some very big radius, collapsed down to its present radius, how much gravitational potential energy would it have released? Virial theorem says half that goes into radiation, although if you're just making a back-of-the-envelope calculation, that's not too important. Divide the total amount of gravitational potential energy the sun released by its luminosity, and that would tell you how long the sun could shine steadily at its current brightness if it were as a result of gravitational contraction. Answer around 10 million years. Well, that means that that can't be what powers the sun long term because of the fact that the sun's a lot older than that. But protostars are in fact powered via gravitational contraction. Main sequence stars are powered via nuclear fusion, but protostars, once they reach quasi-equilibrium, their luminosity comes from gravitational contraction. So there is a time period when the Kelvin-Helmholtz mechanism is the source of the star's energy. That's the bottom line here.
Is that just because it's not hot?
It's not hot enough in the core yet for nuclear fusion, and so it's gravitational contraction that's providing the energy at that part. In fact, notice that on some level it's doing a better job than nuclear fusion because the star is much more luminous as a protostar than it is as a main sequence star. The sun, when it was a protostar, was about as luminous as it will someday be when it is a red giant, as a matter of fact. So it was a lot more luminous back then. Does that mean you would see it brilliantly shining in the sky? Well, yeah, that, but when the sun was a protostar, it wouldn't look very bright from the outside, at least at optical wavelengths, because it was shrouded in a cocoon of and more importantly, dust, right, the dust, which means that it was bright in the infrared, but not visible. Yes. So, once protostar becomes optically thick, rise in T causes rise in pressure P. Collapse achieves quasi-equilibrium. And now is governed by the Kelvin-Helmholtz timescale. And notice that the timescale we're talking about for the sun to reach the main sequence, around 30 million years, is order of magnitude what we got for the Kelvin-Helmholtz timescale from how long could the sun shine with its current luminosity, but you know it wouldn't shine with its current luminosity the whole time, etc. So. Gravitational contraction is the source of its luminosity. So Kelvin and Helmholtz were totally off. As Tef increases, and note when we talk about Tef, that's the effective temperature, that's the surface temperature. And if you got the notes up, you'll just read the notes to say this, but if you didn't read the notes yet, don't. What's the surface, right, for the sun? The surface is the level where the optical depth is, roughly speaking,
2/3.
2/3, right? So that's what we mean by the surface here, the tau equals 2/3 level. Tef is sigma t to the fourth, 4 pi r squared sigma Tef to the fourth is the luminosity, and r is essentially the radius of the sphere that has tau equals 2/3 at its location. As Tef increases, Tef equals T of the tau equals 2/3 level, the opacity of the outer layers becomes dominated by the H- ion due to electrons liberated by metals. Remember, metals are easily ionized, and the sun's continuum opacity is dominated by H-, because remember, H- is hydrogens with an extra electron that's loosely bound, and it's there because metals easily, my eye itches. Man, I cannot continue, just all of a sudden, the corner of my eye is very itchy.
Video discussion.
Yeah.
Why are you watching a video of him talking during?
You'll see during the break.
Yeah, you'll see. Yeah. I want to see if this is still recording. It claims to be, yes, look at that.
Just ask Mark if he's still watching.
Mark, are you still watching? DH. Oh yeah, sounds like it's really good. All right, so what was I talking about? Tau equals 2/3 level. Yeah, H- dominates because remember that extra electron's loosely bound. Anything from this like infrared wavelength of like 1600 nanometers and shorter can ionize it. So the sun and stars similar are dominated by H- in terms of the opacity in their atmospheres. Opacity of outer layers becomes dominated by H- ion. Due to electrons liberated by metals. Where, of course, to an astronomer, if it ain't hydrogen and ain't helium, it's a metal. As a result, the envelope, the outer layers become convective. Because it becomes difficult to transport radiation. Radiative diffusion is not as effective, not as efficient as convection when the opacity becomes this high. So the envelope becomes convective. And indeed, often the entire protostar becomes convective. And in 1961, I forget what the C stands for, but C. Hayashi showed that a fully convective protostar moves along a nearly vertical track in the HR diagram. Called the, what would you guess this track might be called? Like, could it be the Hayashi track, as a matter of fact? Yeah, called the Hayashi track. And that's what's happening at the far right on those evolutionary tracks there. You're seeing these protostars that are fully convective moving down the Hayashi track. After they take a turn, they have to get hot enough for H- to start dominating the outer layers, and then they start moving along the Hayashi track. And essentially, note that when the star later on becomes a red giant, it climbs the Hayashi track. In other words, red giants are nearly fully convective. And so later on, the sun will kind of have a repeat performance where it climbs the Hayashi track, but as a protostar, it descended the Hayashi track. contour, that's right, yes. Okay, any questions? Because I'm about to erase all this. Wait, happy? I'm gonna do it. I'm gonna do it. Here it goes. Do it. So let's look at a one solar mass star. Let's very qualitatively draw its track. So here's the ZAMS, not to be confused with YAMS. What's ZAMS again?
Zero age main sequence.
Zero age main sequence, right? So when it hits the zero age main sequence, it's a newborn, cute little gigantic baby star. So note qualitatively that the track kind of does that. Kind of goes wee down the Hayashi track and then whoop, turns up for a while, whoop, turns back down again and settles onto the main sequence. And there's a figure in your book that has certain points labeled, and the ones we'll be most interested are the ones that in your book are labeled 2, 3, and 5. So I'm skipping some obviously here. And point 2 is 1 million years after the start of collapse. Point 5 is 9 million years after the start of collapse, according to a computer model that the figure that is from your book is based on. And point 5 is 25 million years from the start of collapse. So let's talk about these interesting points along the way. Point 2, protostars fully convective during the first million years of collapse. Start to get nuclear fusion at point 2, it's deuterium burning. Deuterium burning begins due to the large cross section. Deuterium is really readily fusible. Said deuterium is stellar baby food because it's the first nuclear fuel that the star burns, but is there a lot of deuterium available? No, so it doesn't last very long. Low abundance limits epsilon, the energy generation rate. Remember, that's the energy generation rate per kilogram that we talked about long ago. So collapse is merely slow to learn. Now, a planet is something that doesn't have a mass to ever burn deuterium. What do you call, do you remember, what do you call something which has enough mass to burn deuterium, but it doesn't have enough mass for the core to reach 10 million Kelvin and start the full proton-proton chain? So if you're in between a planet and a star, you're a
Failed stars?
well, you're a failed star.
Brown dwarf?
You're a brown dwarf.
Oh.
Brown dwarf is the magic word here. brown dwarf, if you're between about 13 and 80 Jupiter masses, you got enough mass to burn deuterium for a while until you run out of it, but not enough mass to ever undergo the full proton-proton chain and become a main sequence star. So brown dwarfs are in a twilight zone between planets and stars, if you will, but there's probably quite a lot of them out there. Point 3, where it takes the turn there. Increasing central temperature causes decreasing core opacity. Remember that Fermat's law says that the mean opacity is proportional to rho times the temperature to the power of minus 2.
3.5?
3.5. 7/10. Yep, minus 3.5. So as the temperature increases, the core opacity is decreasing. Fermat's law says that. And that means the core turns radiative because the opacities drop down. So radiative diffusion becomes more efficient. So it becomes radiative rather than convective. So that means energy escapes from it into the envelope more readily. That says the luminosity rises. But the star is still collapsing, it's still shrinking. So if L is going up and the star is getting smaller, it has to be that the surface temperature is rising, right? Because 4 pi r squared sigma t to the 4th is the luminosity. So if the R is going down and L is going up, T better go up to compensate for the decrease in R. So in other words, we're going to get a leftward and upward turn. So that's why at point 3, we start going left and up. In other words, on the HR diagram. And it turns out that right about the same time is when nuclear reactions begin in earnest. We're still not on the main sequence yet because we still haven't started the full sequence of nuclear reactions. We get the first 2 steps of the PP1 chain. up to the production of nitrogen-14. So bonus, if you remember, what are those first two steps of the PP1 chain? First is proton plus proton becomes deuterium, right? Because one of the protons turns into a neutron and spits out a positron and a neutrino in the process. And then the next step in the PP1 chain is that deuterium smacks into a what and becomes a what?
Proton.
Proton
Helium-3.
to become helium-3. So we start generating helium-3, but we're not quite hot enough yet for helium-3s to fuse to make helium-4, because the helium-3s have two protons, makes it harder for them to overcome their electrical repulsion for one another. But we do get the first two steps of the PP1 chain. It starts practicing, basically, for when it becomes fully fledged. Due to strong CNO cycle T dependence, the core becomes convective again. So after a bit, the core becomes convective. I'm going to erase the stuff under point 2. Leave the point 3 stuff for now. Point 5. So at this point, the nuclear energy generation rate becomes large enough that it makes the core expand. And if the core is expanding, then that means that it's doing work, you're doing work against gravity. So epsilon sub gravity becomes negative because you're expanding the core. So that means that you have to put in energy to do that. So epsilon for the nuclear energy generation rate increases. That makes epsilon gravity negative because the core is expanding. And in fact, the luminosity of the star drops because even though you're generating more energy by nuclear reactions, you're actually using so much of that to expand the core that it reduces the luminosity overall. Epsilon nuclear becomes so large the core expands. So we're, in the royal sense, the royal we are doing work against gravity. So the energy generation rate due to gravitational collapse actually goes negative because it's not collapsing, the core is expanding. Epsilon gravity becomes negative, negatory. So the luminosity actually drops. Decreasing towards the main sequence value. So in other words, 5 is where we begin that final descent, coming in for a landing. Are we cleared for a landing on Zans? Yes, we are.
I like how it just lands straight down.
Straight down, that's right, yes. Well, it turns on retro rockets right before it hits. And it's a nice gentle touchdown. But it does, I mean, for a while, it was dust everywhere at that point, but. All right, so. When the core carbon-12 is exhausted, no more of that, well, not so much of that pesky CNO cycle anymore. The full PP1 chain takes over. Star settles onto exams. And it's like a movie. A star is born. Aw, the sun was so cute. It was a brand new evening sequence start. Can I erase the 0.3 stuff? So that's for a one solar mass star, that's the sun being born. How about that half solar mass star? Notice it doesn't have the kink at 0.3 where it climbs back up and then lands back down again. It's always decreasing in luminosity. There's no point at which the luminosity rises because the core becomes more transparent, and so extra energy starts getting out to the exterior. That doesn't happen for the 0.5 solar mass star, so let's talk a little bit about that. For the half solar mass star, carbon-12 is never burned in the core because it never gets hot enough. The sun gets something like 10% of its energy from the CNO cycle. A half solar mass star doesn't get any of its energy from the CNO cycle. It's not hot enough. And for this star, temperatures stay cool enough, and thus the opacity stays high enough that the star stays fully convective, so it's always on the Hayashi track pretty much, so it follows it all the way down to the main sequence. Temperatures stay cool enough. And thus opacity high enough that the star stays fully convective and thus on the Hayashi track all the way down. So it doesn't have that kink at 0.3. There's no 0.3 for that star. High mass stars, we have to say, well, what's with the horizontal tracks? Why do they turn horizontal and just kind of scoot over to the main sequence? And notice that when they leave the main sequence, as we said before, they also kind of do a repeat performance. They move horizontally on the HR diagram very nearly after they leave the main sequence. So it's interesting that it's not a perfect retrace, but there is, somewhat partial retracing of paths when both when stars are protostars, before the main sequence and after the main sequence. High mass stars. In this case, the core temperature rises much more rapidly, and so you get carbon-12 burning and the first two steps of the PP1 chain early on, and that makes them leave the Hayashi track because their cores no longer are convective, they're not fully convective anymore. So off the Hayashi track they come pretty high up, and then they move horizontally after that. Central T. Quickly gets high enough that carbon-12 burning and conversion of hydrogen to helium-3, those first two steps of PP1, begin while star is high up on the Hayashi track. Star leaves it and follows a nearly horizontal track. Pretty much keep constant luminosity as they collapse towards the main sequence. So unlike a low mass star, where it's actually releasing more energy as a protostar per unit time from gravitational contraction than it does when it's a main sequence star burning hydrogen in the core, these guys keep nearly constant luminosity until they switch from gravitational collapse to nuclear energy generation of the main sequence. And, excuse me, any questions? Because that's the end of our coverage of protostars and all that kind of good stuff. And now we're going to move on to the Milky Way and to galaxies. So we're going to treat chapters 24 and 25 together. So we'll talk about both the Milky Way and galaxies in general together rather than exclusively talking about the Milky Way and then exclusively going on to other galaxies. Okay? And as is their tradition, why we'll begin. What's that?
Crash course?
Huh? What?
Crash course?
Crash course, that's right, crash course, yes, that's what I was gonna say. I just didn't hear you say.
You were giving me a weird look as
I thought you said Kepler's or something like that. What?
I see a mosquito in here.
Kepler's laws for
There's
gravity.
a mosquito in here?
Yeah, I just watered them down.
Oh,
Here for
wow,
about a
well,
week.
thank you for that, because I don't approve of mosquitoes.
Now he's not, well, he's
Still
still
working.
here, but
Yeah, well, she probably.
that's
Because-
true.
Because it's the females that take.
Oh, I don't
the-
know that mosquito's pronouns, so.
Well, that's true, maybe.
I am
but-
imposing our ideas on
Yes.
a bug.
Okay,
So-
I believe its pronoun is or something along those lines. All right, so let's present. So Mark, I'm gonna stop the video here, and you're just gonna watch this on the what's it called, the presentation, and then you're gonna come back afterwards. What?
Let's make fun of Mark while we can't see.
Oh, we would never do that because Mark is awesome.